Okay, so we ended off yesterday talking about the lunar eclipse and calculating the net force of gravity acting on the Earth. The moon was pulling it one way, and the sun was pulling it the other way, and they create a happy balance that makes life on Earth possible of 3.51 times 10 to the 22 newtons worth of force towards the sun. Okay? Now, the idea of universal gravitation is fairly straightforward. Like in terms of understanding, we really only need to understand two things. More mass, more gravity; more distance, less gravity, exponentially. And that's really about it. Okay? The rest of it is calculations and algebra. And none of that's terribly difficult either, other than making sure you press all the right keys and put in the right amount of brackets. That's the trickiest part, really. Okay? Now, I say that, and then we're going to do a question like what we did yesterday about net force and gravity, but now the moon is off at a right angle. Okay? Now remember, net force is the vector sum of all forces. And now the moon's force is perpendicular. What do I have to do with vectors when I want to add them? Draw them tail to head, right? Okay, so here's the good news. You don't have to recalculate the numbers. The numbers are the same. So when you calculated that force of gravity between the sun and the earth, I think it ended up being 3.53 times 10 to the 22 newtons. And the one for the moon and the earth was 1.99 times 10 to the 20 newtons. Can you tell I've done questions like this involving the earth and the moon and the sun a lot? But I actually remember those numbers. Okay? So much useless information crammed in my brain. All right, so those are our forces. But now, earth, moon, and sun are aligned like this. Right? I want you to see if you can calculate the net gravitational force acting on the earth, magnitude and direction. Okay? Give you a couple minutes on that one. So what we're going to have here are two forces, okay? And we're going to have one of them being the force of gravity between the sun and the earth, okay? And then we're going to have the force of gravity between the moon and the earth. And that's not to scale. That line should be even smaller than that by comparison. Okay, it is like nearly 1,000 times less than the other number. Okay, so it has to be incredibly small, which is why the angle in your answer is so incredibly small. It only deflects the Earth's movement 0.3 degrees. Okay, but it's doing that constantly, right? As it moves around, it's constantly pulling the Earth in different directions. So that means then that my net force is going to be the hypotenuse of this triangle, which is going to be virtually the same length as the longest side, as the other longest side. Okay, so I'm going to go and do Pythagorean theorem here because they're at right angles to each other. Put those two numbers into my calculator. So square root of bracket bracket. Let me see, 3.53. 22 squared times 1.99 20 squared.
Are you supposed to add?
Oh, I just did the plus sign. I was going to say that number seems really big. Slightly problematic. Better. Okay, so basically it doesn't even change the number, right? Like those two sides are virtually identical. Right? So now when I do the trigonometry calculation, I'm going to use the adjacent side and the hypotenuse to get that angle. Right? So I'm going to go inverse cos of the opposite side, which would be 3.23, sorry, 22. Divided by this number. And I get 0.3 degrees off of towards the sun. Okay, probably be my vector. Okay. I have basically never put one like that on a unit exam that I can remember. Maybe I did it once. Okay, but as long as you understand that whole net force, sum of all forces thing, you'll be good with a question like this. Okay?
Can this be a bonus?
I don't like putting bonus questions on tests. You know why?
Why?
People spend too much time on them. And then I find that they're like missing stuff that's really important on the test. Yeah. I used to do it, but I found that there was too much of a problem with people finishing the test. They obsess over the bonus question. Plus then it makes it possible to get more than 100, which is not possible. I can't stand seeing that. Oh, I got 103% in math. How mathematically do you get more than 100%? By definition, 100% is the maximum you can get. Yeah, that's my beef. Rant over. Okay, everyone okay with the gravitation questions? Okay, there's nothing too terribly complex. All you got to do is manipulate FG. Okay, solve for either R or one of the M's. You'll never have to solve for big G because you always know it, right? Okay, and remember the significant digit thing, right? If all the numbers you use are off your formula sheet, you can have as many or as few significant digits as you want on your answer, okay? Because everything is an absolute, right? In the quiz questions today, you got values given to you. Those are considered measured values, okay? But if you take them off your formula sheet, they are considered absolute. All right, well, let's talk satellites. Okay. So with satellites, okay, the idea of getting something to orbit the Earth has been around since Newton's time. Okay, in fact, Newton got to the point in his career where his ideas were beyond what could be tested experimentally, given the technology of the time. Okay, so he had these ideas he wanted to test, but there was just no way to do it because the technology wasn't there. So he started doing thought experiments, okay? And I mean, you know that people think highly of you when you can say, I thought this thing up, and it's really cool and it'll totally work, and everyone will go, okay. You're Newton, so yeah, that's fine. You did that experiment in your head, right on. Any sources of experimental error? No, I'm Newton. And that's, you know, so yeah, he got to that point in his career, okay? Now, his thought experiment for getting something to orbit the Earth went something like this. I put a cannon on top of a really tall mountain, and if I can shoot the cannonball fast enough, it will orbit the Earth. Absolutely 100% correct in theory. The problem with making something like a cannonball travel through the Earth's atmosphere at a speed necessary for that to happen, the cannonball would have to move at 8 kilometers per second, which would most certainly cause it to ablate completely. That means burn up, okay, due to friction. All right? That's why we worry about when our spacecraft are re-entering the Earth's atmosphere. They are moving at incredible speeds when they are in orbit around Earth. And so as a result, they're going to have a lot of friction when they encounter the atmosphere, right? Even our fastest aircraft can get very, very hot. Again, if you've seen Top Gun, where he basically gets the aircraft so hot from going Mach 10, which that's crazy. Anyway, that's actually what the problem would be. Okay? Even the SR-71 Blackbird, the fastest aircraft produced, okay, they had to cool it before the pilot could get out. Where they have to use asbestos gloves to get them out or touch the aircraft because it would be so hot after traveling even Mach 3. Okay, so high rates of speed cause things to get very, very hot. Okay. All right, so this was his idea. If I can launch this cannonball and it goes fast enough, it will go far enough in the first second that the distance it falls, which would be 4.905 meters, would be accounted for by the amount the Earth curves away. Because even Newton at the time understood the Earth was round. I know I keep coming back to that, but I can't help myself. Okay? So he understood that if the Earth curved away and you go 8 kilometers, the Earth would curve away the distance that the object would fall. And that means that it continues to fall, but never gets closer to the Earth. and thus would orbit the Earth at a constant altitude, which is why you had to fire it from the top of a tall mountain. That way nothing would get in its way. Okay, everybody all right with that idea? Okay, this is the principle behind all satellite motion. We still use this idea today. Okay, we just understand that you have to put satellites outside the Earth's atmosphere for this to be practical. Okay, even in low Earth orbit, they have to go very fast. Okay, the farther away you go, the slower you can move. We figured out the other day that the moon only goes 1 kilometer per second, and it stays in orbit around the Earth. Okay, but it's much, much further away. Right? So high Earth orbit doesn't require as much velocity. Low Earth orbit requires more. Everyone all right with that idea? Okay, so that was the challenge early on during the space race, was to build a rocket powerful enough that wouldn't explode on its own, okay, to get a spacecraft into orbit at a speed necessary to maintain orbit. Who did it first? The Russians, yeah, okay. Sputnik was the first man-made object to orbit the Earth. It looked like a basketball with antennas coming out of it. Okay? And it orbited the Earth a few times and went beep, beep, beep. And it scared the living tar out of everyone. Because, of course, at the time, the Cold War was in full force. Okay? And if you could put something into orbit, you could put a bomb in orbit. And you could drop it on anybody, anywhere in the world. And that's true. That's how intercontinental ballistic missiles work. Okay, they are basically low Earth orbit vehicles. You put a nuclear warhead into low Earth orbit, and then you make it fall out at the appropriate time on whatever unfortunate person is your target. Okay, fortunately, not very many countries in the world have that ability. Okay, we're very fortunate that way, but enough do.
Does the U.S. have that ability?
Yes, they do. The U.S., Russia, China. UK, France, India, I said China already, right? Yeah. And North Korea is working on it.
What about Canada?
Canada does not have any nuclear weapons. John G. Diefenbaker said Canada would never have nuclear weapons, and we have never built nuclear weapons.
Wasn't it like a Canadian who made the nuclear bomb or something?
The uranium used in the first nuclear bombs was mined in Saskatchewan.
How did nuclear bombs even work?
You basically make the atoms split. There's 2 explosions. A small explosion that causes the fission reaction, and then the fission reaction that creates the mushroom cloud that annihilates all things. Has anyone seen the movie Oppenheimer yet? I gotta go see that. Oppenheimer was the scientist that helped develop the nuclear weapon. And this is totally true, but they weren't sure when they first detonated it whether it would trigger a chain reaction that would burn the Earth's atmosphere. Yeah, and they tested it anyway, because it was only a non-zero chance, which meant it was very small, but it wasn't zero. It's actually in the trailer. If you ever watched the trailer, Matt Damon delivers the lines like, "Not zero." Well, what's wrong with not zero? It's not zero. Yeah, annihilate the entire Earth. Let's test it anyway. That was the time they lived in. It's hard to think which one's worse. Which one's scarier? Okay, so this is the idea behind satellite motion. Now, the thing about this is that it's just like what we did yesterday with the speed of the moon. The centripetal force that causes the object to orbit, which is a circle, okay, is provided by the force of gravity. Okay? And we set those 2 forces equal to each other in formula form. mv squared over r equals big G times mass 1 times mass 2 over r squared. And as we said yesterday, one of those masses cancels. Okay? And it is the mass of the satellite. Okay? The orbiting mass is the one that cancels. The central mass stays. Okay? And the reason for that is this is the mass that moves in the circle in this formula. Okay? So that has to be the satellite, and it will cancel off both sides. That also means then that mass is irrelevant. Mass of the satellite, that is irrelevant for any given altitude. Right? So we can have the International Space Station at that altitude, it has to move at a certain speed. We can put Sputnik, which is way smaller at that altitude, it has to move at the same speed. Okay? The speed is independent of mass. Now, the other thing that can come up, because we often get this with satellites, is instead of getting the speed, or being asked to get the speed, we're asked to calculate the orbital period. Okay, so the time it takes for one orbit. Now, sometimes you can just calculate v and then plug it into this and solve for t. You're doing 2 steps, but you can do it that way. But there's a possibility that some mean physics teacher might make a question where it's impossible to do that. And then you would have to do this. How many people remember this term from math? Substitution. Okay, so you would have to substitute this formula into this formula for v. Okay? It's not that hard. The real trick here is in that formula, v is squared. So what do I have to do to its whole formula?
Square.
Right. Okay, so this whole formula, squared, what's 2 squared?
4.
Okay, what's pi squared?
9.
Pi squared. What's r squared?
R
R
square.
squared. See, it's easy, right? Okay, what's t squared? T squared. Okay, so there's that formula squared. Now I just punch it into this formula in place of v, okay, and it looks like this: m 4 pi squared r squared over t squared times r. Okay, I literally just, like, it's like that kid that forces the puzzle piece into the puzzle, like smashing it in. That's what we're doing. We're smashing that formula right into the other formula. Okay, now the only thing we have to watch for here, there's an r squared in the top and an r on the bottom. What happens?
So the r on the bottom disappears and the square on the top disappears.
Got it. We've substituted that formula in. The reason that would happen would be this. I give you the orbital period and I ask you to calculate the radius. Okay? If that situation happens, you cannot do this in 2 steps because you'd need the radius and you wouldn't have the speed. Okay? So you wouldn't be able to do it in 2 steps. Okay? So you'd have to substitute where you take v right out. Okay? All right, so we'll start looking at a few kind of example ones here. Okay? All right, so these were kind of Newton's ideas. They're modernized diagrams, but okay, you know, you could make something go fast enough. It's basically, a satellite is just a projectile, right? If I don't make the projectile go fast enough, it follows a projectile arc that encounters the Earth. Okay, same with this one, not quite fast enough, not quite fast enough. But if it goes fast enough, that projectile arc just completes the circle and comes all the way back around. Okay, that means then that a satellite is always falling. Okay, so if you are in orbit, you are always falling, which is why you feel weightless. Okay? Chris Hetfield in all those videos we watched, he's not weightless. Okay? He's attracted to the Earth, and he's always falling towards it. But you always feel weightless when you're falling because there's no what? There's no normal force. Okay? And so because he's always falling, he is in what we would call 0G, or apparent weightlessness.
Would it not go into, like, if you're falling though, would it not go into, like, negative? Would you not, like, go to, like, want to go to, like, the top if you're falling?
No, you're falling at the same rate.
Oh, okay.
So it'd be like falling inside an elevator.
Right.
Okay? I'm sorry, I don't mean to, like, scare anybody, but if you were inside an elevator that was falling, you would fall with it.
Yeah.
Okay? Like, if it breaks loose, yes, you'd feel weightless, but you'd also still be on the floor.
Yeah.
Right? I mean, you might move maybe slightly or something like that, but you wouldn't fly up to the ceiling.
Yeah.
Yeah. The elevator would have to accelerate downwards for you to fly into the ceiling at a
Right.
rate different than you were.
Right.
Yeah.
What would your guts not feel like they're?
Oh yeah, you'd feel weightless, right? Because if you're falling at the same rate as the elevator's not gonna push
No, I'm
on you.
saying, like, in the satellite in space, wouldn't you feel like your guts are inside your?
Yeah, it takes a long time for them to adjust, like several days before they're not just pukey.
And would that feel different than actually going, like, out into space and feeling 0 gravity, or would it feel the
No,
exact
feel
same?
the same.
Okay.
Apparent weightlessness and actual weightlessness are gonna feel exactly the same.
Okay.
Okay.
So with the mass thing, for example, if there wasn't like the atmosphere, could you technically put like a marshmallow into orbit or something?
Mm-hmm. Anything. Yeah. Absolutely anything it would work for. Yeah, marshmallow, a pea, whatever. Okay. The only problem is with a marshmallow, you got gases trapped inside it, right? You put it out in the vacuum of space and yeah, do what lots of things do in space, explode. All right. So a satellite that is always the same height above the Earth, okay, moves with uniform circular motion, and okay, we know that we can set it up like this. So that's what we just went over there. There are different kinds of orbits, okay, around the Earth. There are equatorial orbits that go around the equator. There are polar orbits, okay, that go around the Earth this way, right, which are a little bit different because remember, the Earth's not perfectly round, so the orbital distance is always changing when you go around the Earth vertically. Okay, it's not vertical motion, but because the Earth gets wider at the equator, your speed actually changes in a polar orbit. Okay, you've got bound orbits, and then you have unbound orbits. Unbound orbits are ones that could escape the Earth or the Earth's gravity well, and that's what we use to launch things to other planets, okay, or the moon, as the case may be. All right, what do we call an orbit that stays over the same spot on Earth?
A circular orbit. Fixed.
What?
Fixed orbit?
It's a type of fixed orbit. It has a specific name. I stay over the same spot. Geosynchronous. You guys haven't heard that term before? Okay, so a geosynchronous orbit is the type of satellite that stays over the same point on Earth all the time. So that means then that its orbit would take how long? 24 hours, right. Okay, its orbital period has to be the same as the Earth's period of rotation, so it stays over the same point on Earth. All GPS satellites, all communication satellites, so the stuff you get satellite TV from, okay, all of that stuff, those are all geosynchronous satellites, and they are in high Earth orbit. In order to have a period of 24 hours, you have to be much further away from the Earth. Okay? The International Space Station has an orbital period of, I think it's 92 minutes. Okay, it goes around, they get 18 sunrises and 18 sunsets a day, right? They're going around the Earth tons and tons of times in one day, okay? That's not good if you're trying to communicate with one spot on Earth, because half the time, or more than half the time, you're going to be on the other side of the planet, where you don't have a straight line of sight to your target, okay? And this is how satellite TV worked back in the day when it first came out, okay? Anyone ever seen those old satellite dishes? Right, they're like 6, 7 feet across, okay, and they're motorized. They would have to move to keep tracking a satellite because the satellites weren't in high Earth orbit, and so they'd have to track and follow a satellite. And this is where it really sucked. Game 7, overtime, Stanley Cup Finals, satellite dish, following the satellite, following the satellite, following the satellite. Satellite goes over the horizon. Now what? Now it's 30 seconds for your satellite dish to go and come back and reacquire the next one coming over the horizon. Okay? So you'd have these gaps in coverage that would always happen at the most inopportune times. Okay?
How many satellites are surrounding the Earth?
Tons. I have no idea how many, but it's probably thousands.
Really?
Yeah. Yeah. It's now gotten to the point where when you want to launch something, you have to check and make sure where you're going to put it isn't where something else is.
So 100 years ago today, though, there was 0.
Yep.
And now there's thousands.
Yep. I mean, lots of companies launch their own private satellites, and there's a bunch of satellites that are secrets, right? That,
Wasn't there a point where, I don't know, I'm mistaken on this, but I don't know whether it's right, but you wanted to have like a sky full of like satellites or something like that. I don't remember how it
Is
worked.
Starlink
Yeah.
Wi-Fi.
Starlink Wi-Fi.
Yeah.
So satellite internet.
You're supposed to be able to get Wi-Fi anywhere in the
Anywhere
world.
anywhere in the world. I mean, you can sort of do that now. You can get a satellite mobile phone that will talk to, like, it'll just works anywhere because it's on satellite. Same as a emergency locator beacon, right? Like those work on the same principle. You just have to pay enormous sums of money for the data, right? Because in rural areas, you can get satellite internet.
Yeah.
Yeah, it's the same idea. It's just probably not as readily available or fast. Okay, so let's talk about, so these geosynchronous orbits, like I say, they make sure that the satellites stay over the same place on Earth, and we use that for you know, if you're using Google Earth to navigate somewhere, okay, your satellite navigation system, satellite radio, and if you got like Sirius, you know, or something like that in your car, all of those things operate off of satellite signals from orbit.
There's 7,702 active satellites.
There you go. We were right, thousands of satellites. Now, you gotta remember, there's a lot of space in space. That's why we call it space, okay? So, you know, the likelihood of running into anything is probably pretty low, but when it's billions of dollars worth of material, you probably won't wanna go, it's probably okay. You probably wanna be sure. All right. All right, so if we want to find the period of a satellite, then we have to do this substitution thing. So that's what we just talked about there, okay, putting in the substitution factor, okay, and we'll do a couple like that as well. Okay, and as we said here, the orbital period and the orbital velocity are independent of the mass of the satellite, so it doesn't matter what the satellite's mass is, at x altitude, it must move at x speed. Okay, okay, so once you put a satellite in orbit, do you need to do anything else with it? You shouldn't. Okay? It shouldn't require any more fuel. Okay? It shouldn't require anything like that. It should just be able to do its thing, okay, and stay in orbit. Now, the reality is that there's probably going to be some fuel and maneuvering ability on board in order to turn the spacecraft if it needs to be turned, okay, things like that. But for the most part, you're not going to need to have major amounts of fuel on board to do maneuvers because it's just going to stay put. Okay, in that orbit where you put it. Now, on the other side of that, it does still need to power itself. Okay, what do most satellites run on? Solar power. Okay, why are there no nuclear powered satellites, or not supposed to be?
Just in case, like maybe like asteroids or comets hit them or something, they blow up.
Yeah, I mean, satellites fall from orbit periodically. You don't want a nuclear powered satellite falling from orbit and spreading radioactive material over a large area as it burns up. Okay, so that's certainly a concern, which is why they have to be powered by something other than that. There's an actual treaty in place that prevents or forbids nuclear material being in orbit, okay? Except for experimental purposes, and then it's like super controlled and whatever. But, so most of them operate on solar power, okay, which is great when you're above the Earth's atmosphere because there's really nothing to get in the way of it.
What causes them to fall back down to Earth if they're in orbit?
Well, Earth's atmosphere is not a ball, right? It's not a perfect ball, and sometimes there's, you know, changes in pressure and stuff like that that can cause protrusions of the atmosphere, and so they can encounter bits of things that cause a little drag and slow them down a little bit.
So there's lots of factors.
Oh, lots of factors, yeah, for sure. And that's why you always have to have a little bit of maneuvering ability if you want your satellite to stay in orbit. You either have to put it high enough that that's not a problem, or give it the ability to move around.
Right.
Okay. And some satellites are not permanent, right? Like spy satellites have to be able to move. They have fuel on board, and they are expendable, okay? Because they might get shot out of orbit, or they might just run out of fuel and have to be deorbited, okay? And we do deorbit satellites occasionally, okay? In order to just, oh, well, it's not working anymore. It's too expensive to go get it, so we just deorbit it.
How do they deorbit it?
They'll use any fuel left on board to run it into the atmosphere in a controlled way.
Okay.
And the bulk of them burn up in the atmosphere before they ever get to the Earth. And if they don't, they usually try and crash them into the ocean.
Can they ever fly away?
They could certainly fly away, yeah. I don't know that any have, but they could.
So was that one, was it a camera satellite thing that they took down recently or something like that? Was it a big deal? I forget what that.
Like shot it down?
No, they didn't
Oh.
shoot it down, they like brought it down and then they replaced it with a better one, something like that. It was a big deal or something.
The James Webb Telescope.
Yeah, did they deorbit Hubble?
I don't know if they deorbited Hubble.
Yeah, no, I mean, the James Webb was supposed to replace Hubble. But I don't know if they deorbited Hubble after that or not. I didn't look into that. But that's the new one, is the James Webb one, just telling us tons of cool stuff about space, because it's just amazing. And it's got all those little hexagonal mirrors, right? And it had the same kind of luck that you have when you get your windshield replaced. What happens the day you get your windshield replaced?
Cracks.
You get a crack in it, right? Well, the James Webb Telescope, when it was opening up, a small meteoroid hit one of the mirrors. So it has like a little flaw now, like on the very first day. Yeah. It's crazy. That's the kind of luck. Okay, so let's look at a few examples here. This one we did yesterday, so we won't do that one again, the speed of the moon in orbit around the Earth. Okay, but let's let's try these two. They're both, well, one's radius, one's speed. Okay, so they both use this. Okay, and neither one of them will need substitution. Okay, so with our first one here, we're told Neptune's average orbital radius, so we're given r, okay, and we're told the mass of the sun, which we already have on our sheet, okay, we're looking for Neptune's orbital speed. All right, so we got mv squared over r equals big G times the mass of the sun times the mass of Neptune over r squared. Which mass is this?
I don't know.
That's m2, which in this case would be Neptune. Neptune is orbiting the sun. It's always the satellite that is going to cancel.
And that's how we know it's.
That's how you, yeah. So this one's always the one moving in the circle. Okay, so in this case that's Neptune. Neptune's mass is the one that is going to cancel off. All right, so we're looking for V, so I'm going to bring r over to this side. When I do that, r cancels off the square, and I only have a regular r on the bottom, and then I will square root all of that. So I'll have the square root of big G times the mass of the sun over r. All right, so when we plug in our numbers here, that'll be 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, the mass of the sun, okay, and divide that by 4.5 times 10 to the 12. Okay, and when we do that, we should get 5.43 times 10 to the 3 meters per second. Okay, so Neptune is moving in its orbit at 5.4 kilometers per second. Okay, is that pretty fast? Earth's faster, okay, because Earth is closer to the sun. The closer you are, the faster you have to go, or you'll fall in, and we definitely don't want that. The sun is kind of a big fire. Okay. All right, everyone okay with number 2? All right, now this one involves orbital period. Okay, so we'll walk through this one together because we haven't done one like that yet. Okay, so Landsat is an Earth imaging satellite that has a polar orbit, okay, and it's at an altitude or height of 912 kilometers. What do I have to do right now? Because I just saw one of those key words.
Oh, we have to do substitution.
Well, I will have to substitute, but I don't want to do it yet. I have to add it to the radius of the Earth because the radius of the orbit is center to center. Okay, so I got to take my 6.37 times 10 to the 6 and add 912,000 meters to it. Okay, so that's the first thing we should do. If you see those keywords above the surface, height or altitude, you are either adding or subtracting the radius of the planet. All right, so 6.37 E6 plus 912,000 meters. All right, so there's our radius, 7.282 times 10 to the 6. Okay, so we want to find the orbital period. Okay, one of our other givens is mass of the Earth, 5.98 times 10 to the 12. Not 10 to the 12, 10 to the 24 meters, okay? And that's it. That's all we know, and that's enough. All right, so we're gonna say FC equals FG, and that's gonna be mv squared over r equals big G times the mass of the Earth times mass 2 over r squared. All right, I don't have V, and I'm being asked to calculate the period. So V equals 2 pi r over t. I want to substitute that in for V. What do I have to do to the whole formula? Square it. Okay, so that's going to mean 4 pi squared r squared over t squared. All right, and then this is what I'm going to do. I'm going to erase the V. I'm going to pull this. Oh, I don't want the whole thing. All right, this might not work now. We'll try it. Okay, I just substituted it in there. All right, I just have to do one more thing, and that is I have to cancel this and this off. now what else can I do while I'm erasing things? Right, I can cancel the mass of Landsat, thankfully, because they didn't even tell me what it was.
There's a square on the arm. On the bottom.
I did, no, not this one yet.
Oh, yeah.
Right? Okay, so I'm looking for t. Now, t is on the bottom. If I'm going to solve for it, it needs to be where? On the top. So this manipulation is about as involved as they will get. It's just algebra, it's just multiplying and dividing, but there's a lot of it. All right, so t squared's on the bottom, I want it on the top over here. I'm going to multiply both sides by t squared. Okay. Now I got to move everything else over to this side. So I'm going to have to multiply both sides by r squared. What's r squared times r? R cubed. All right, and then I'm going to divide both sides by big G times the mass of the Earth. Or sorry, divide both sides by big G times the mass of the Earth. All right, that solves for t squared. What do I want? T. All right, yep, that's about as involved as the manipulating we'll get in this unit. Okay, so now we plug in our numbers here. So 4 pi squared times 7.282 times 10 to the 6 cubed divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. All right. If you thought the stuff we were already typing into our calculators was a mess, now you get to add a cubed in there on top of it. Okay, so let's move the calculator over here. Okay, so we are going to have, and I'm going to square root this after, so I don't have to have so many brackets. Okay, he says that and then he makes 2 brackets. 4 pi squared times 7.282 E6 cubed. In case you don't know how to do the cube, hit the math button and then press 3 and you get the cube. Math and 4 gets you cube root, which you'll need if we ever have to solve for radius using the same method.
Press the exponent button and choose 3.
This exponent button?
The one up there.
Which one?
Above divide.
Above divide. Yeah, I don't like doing it that way. I'm kind of old school, I don't like that. I always find people mess it up. Just me. It's a me thing. It's an ish me, not an issue. All right, so there's the top, okay, and here's the bottom, 6.67 e negative 11, and 5.98 e 24. Okay, oh, now I gotta divide those 2 numbers, I forgot to say divide. That number divided by that number gives me that, and then I gotta square root that. Okay, so Landsat has an orbital period of 6,182 what? Seconds. Okay, so just under 2 hours, like an hour and 40 minutes probably, something like that. 103 minutes. Okay, we'll work a little bit more on satellites tomorrow. Okay, just do some practice stuff. We'll do gravitational field strength on Tuesday. And then we're pretty much done. So I think your unit review posts today. I think I have it set to post today or posted yesterday. Okay, so you can have a look at that. And that's kind of the plan going forward. Okay?
Being out in the